Visual node-based programming, editing, modeling, diagramming kinds of systems have become very popular across a wide range of industries. For example, here on the screen we're looking at a tool called FilterForge, which is a really neat application that allows a non-programmer to create really elegant filters without doing any programming at all for Photoshop. So something that is normally completely inaccessible to the average artist is now available to them in using this drag and drop iconic format, where they have different kinds of effects that have inputs and outputs, and you take the output from one effect and plug it into the input on another effect and create these chains, and it creates an overall effect that you can then apply to an image. So this is just one example. Artisy is something completely different. This is also a very elegant solution. This is used to diagram story. So if you're creating a story for your movie or a story for your game or whatever it is that you're creating content for, this tool is used to diagram the relationships in the story. And it's the relationships between elements of the story and also characters and effects and audio. And this is just really an elegant tool for being able to see it at a glance, the relationship among the various components in the story. Now, if you're working with a linear media like a movie, then it's pretty easy to see those relationships because they happen in a sequence. But in something like an interactive media, for example, an advanced simulation, then creating the content and seeing the relationships in different branching and relational aspects can be very complicated. And this is also a great tool for many editors to share one common visualization that everyone can access and edit. Here's an example of a tool similar to that being used in editing music. So this is a tool that you can use to control your MIDI device and also edit the final product that you make with your MIDI device. And then on the meta level, these kinds of node-based modeling tools are very popular with companies that have to do large-scale visualizations. So, for example, this is a open model source code visualizer for a DoD vendor, and it shows at the project level individual nodes, and then you can open up the individual nodes and see the relationship of the subsystems within the nodes, and then you can open up the subsystems and you can see the individual components within the subsystems, and then if there's actual programming applied to those subsystems, then you can actually get down to the source code level itself. So these kinds of systems are very popular, and their elegance and simplicity can sometimes confuse their effectiveness, because this can really be a great way to describe visually to someone your understanding of a concept or an idea. So what I'd like to do next is take a look at, real quick, an actual tool being used, and then finally apply the idea to a very, very simple science concept in terms of how this kind of node-based modeling could be used to both do diagramming as well as perhaps create front ends for students that are working in virtual environments. Here's an example of a node-based scripting programming system being used iconically to execute programming in 3D. So the application that I'm using is Softimage. And in my viewport here you can see that I have a sphere and it's got a gray surface on it. So what I want to do is I want to add some kind of a texture to it. So I'm going to tell it that I want to add an isotropic texture to it, and I'm going to tell it that I want to have some kind of an image that I'm going to apply to it. So now you can see that's been applied. So I can edit this application of this surface material to my model by going into a view that's a node-based editor called the render tree. So now in the render tree I have representation of, here's my image, and my image is this is the name of the image itself found on my hard drive, and this is a plug into my node called image that has a texture, and I can add many textures and blend them together. And the output of my single image is an input to the diffuse layer on my anisotropic shader, and that's being applied, the outputs of that are being applied to my material, which is applied to my sphere. So let's say that I want to make my surface look bumpy, so I want to get a new node. So I'm going to go get a node, and the node that I'm going to get is a bump generator. So now I have a new generator, and I can apply this bump mapping, which is the effect, the illusion of surface disruptions, into my material. Now I have an output here, and it has a little yellow vector type output icon, and I can't see where there's a yellow input, so I'm going to drag this over onto my material and let go, and it'll show me, okay, here's some choices that I have, and I'm going to select bump map, and now it shows me, okay, this is an input now to bump map. And what I'm going to do is I'm going to add a texture onto my bump map, and when I do, then I can cause that bumpiness, so now I can see there's a very bumpy effect that's happening in my render based upon the fact that I just added, you can see the crease right there, I just added this bump generator, and it has this image plugged into it. So that just gives you an idea of, I just changed my image that's being applied, and now I have my image that was being used for my diffuse texture also being used for my bump generator on my sphere. So this is an example of programming, scripting, and it's entirely iconic, and I'm being informed about what inputs and outputs I can use based upon this system. Now I can see over here that what has happened is all of these things that I just executed, these are actual commands that are being done in C# within the interface, so that these things actually happen to the model. So this iconic drag and drop schematic node-based editing format is actually creating command calls that are being utilized within my application. So let's use a very, very simple subject as an example for a node-based model. I'm going to diagram my understanding of how plants grow. So I've just watched a video or read some text or worked with some kind of instruction that has explained to me that there's two major dependencies. I have to have water and I have to have sunlight in order for a plant to grow. So now I'm being asked in a virtual environment to demonstrate my understanding of that visually. So in the normal classroom, traditional classroom, we might have a pen and piece of paper and draw a diagram. So now I have a way that I can do this virtually, and that's to create my understanding in a representation with this system of nodes. So I'm going to start by putting my components out here that make up my system. So I'll start with this component, and I'll call this plant growth. And I'll have another component, and that will be water. And another component, and that will be sunlight. And maybe I need to have some way that I can measure my plant growth, so I'm going to have a component called a meter. And maybe I'll have another component that is my input controls, so I can test and make changes and run experiments. So I'm going to call this a water variable, and I'll make a sunlight variable. Now there are lots of other components that are part of this model that we're not going to look at, so we're not going to talk about CO2 being released and water vapor being released and sugars being created and the amount of photosynthesis and everything else. We're just going to look at these two dependencies, water and sunlight, and how they are affecting plant growth as a diagram of a system. So I'm going to say in order to have plant growth, I need to have both water and sunlight. So I'm going to have an input on my system, and typically in a node-based system our inputs are on the left and our outputs are on the right in terms of the logical flow, the drivers that make the system work in feedback loops. And then on top we have variables, parameter inputs, and on the bottom we have variables, parameter outputs. So I'm going to rename this particular input, and I'm going to call it water. And I'm going to make another input and rename it and call it sunlight. Now I'm going to have an output, and I'll rename that, and I'll call that growth. Now I'm going to say that if I have both water and sunlight, then I'm going to have an output, growth. So my meter is going to have an input that it's going to be looking for to function, and that will be growth. So my growth will turn on my meter. Now in order to have a feedback loop system, I'm going to have an output that I'm going to create on my meter, and I'm going to label that growth. That just tells me that I do in fact have growth that I'm measuring with my meter. We'll see how that works in a second. Okay, so I have a water input and a sunlight input. So from my water component, then as you would guess, I would want to create an input called water. Excuse me, an output. Same thing here. Create an output, and I'll call that sunlight. So I have some sunlight and I have some water. So other conditions, temperature, food, whatnot, we're not going to talk about. We're just going to say that these are the two things that we're concerned with in order to know that we're going to have plant growth. So I have them both present. If they are both present, then the output will be present, and that will drive the meter. So here's a teachable moment. I've created a Boolean AND condition where I need to have both inputs be true for the output to be true, and if any of the inputs are not true, then the output's false. So now I'm going to control the amount of water and the amount of sunlight. So I'm going to create an output here on my water variable, and I'm going to rename that and call that water, and I'm going to create an output here and call that sunlight, and I will be making a input into water from my water variable and an input into sunlight from my sunlight variable. Now how I'm going to control this, I'm going to have a parameter, an amount of water that I'm going to set up. So I'm going to say I'm going to have a floating point number, a number with a decimal point, and I'm going to rename that, and I'm going to call that gallons. And over here I'm going to have an adjustment that I make to my water variable, and I'm going to say that I have a output, again a floating point number, and as you might guess, I'm going to rename this gallons. So now what I do in my representation of my system is I link the parameter that I've controlled of my variable, the amount of gallons, to my input on my water drive. So when I make a change to my water variable, I'm changing the amount of gallons that are being present in the water. So now I can do the same thing here to the plant growth. I can say that I have a certain amount of water that's being present, which I'll call, whoops, don't need to create another input. Actually, I want an output. I can create here gallons, and I can just drive that right into my plant growth. I can do the same thing here. So I'm going to create an output, and let's say I'll call this hours of sunlight, and that hours of sunlight will be driven into here, and I'm going to create an output, and I'll call that hours, and that will go into my plant growth. So now how this system works is I make a change to my variable, the number of hours or the number of gallons. which changes the amount of water being present or the amount of sunlight being present. And now I have two variables. I not only have two drivers, I have to have both water and sunlight, but now how much water do I have and how much sunlight do I have? Now I know I have growth, but in terms of a variable amount, a measurable amount, how much growth do I have? So I can make another output here. Again, this is a floating point, and I can rename this and call it inches. So now I have inches of plant growth. I'm going to drive that into my meter. So now I have inches of plant growth being felt into my meter. And to loop my system, I'll come back and take the output and loop it back into the input. So now I have a system that's operating as I understand it. This is my understanding that I'm showing back to the teachers, showing to classmates. This is how I understand the system of water and sunlight impacting plant growth. And I have a way to conduct experiments. So I can change the variable amount of water, the amount of sunlight, and I'm going to see a corresponding change in the amount of inches. Now I might want to make a comment, like maybe I'm going to make a comment that too much water is toxic, as an example. And then this is a very typical kind of a tool that I would use in any kind of a logic diagramming. So when I share my model with my teacher or a classmate, they can come in and I have these comments that I've made that explain my thinking and how the system works. So at the base level, how this is useful is I'm working in a media, so I don't have a piece of paper, I don't have a pencil, I'm not able to draw, I'm able to work virtually. And this is a system that I can save and I can share it electronically. And I can come back and I can edit it. The next big step is that this can actually be the front-end control system for an experiment that I'm running. So now I want to see how the inputs affect a simulation. So the way that this can be used in that fashion is that the first step that the student does is create a model. This is my understanding of how this works. And then attach this model to the actual simulation. Okay, now you're going to run an experiment. For 30 virtual days you're going to observe plant growth and you're going to make changes to the amount of water being present, the amount of sunlight being present, and this could actually be the system that would provide the information to those variables, and you would record what was being present at the meter. So this is actually a front-end control system for simulation itself. So then it presents two opportunities for the learner. One is the diagramming, the modeling and understanding, and the other is actually having a way to see how that plays out in terms of the understanding being applied to the simulation itself.